I see a lot of new faces. For those of you who don't know me, I'm Sean Law, one of the data scientists here working on the advanced tech team at TD Ameritrade. And I co-organized this meetup with Ben Zeitlin from Anaconda, as well as Marcus Sherman in the back there, and a couple of other folks like Logan Alstrom helping out. But I want to also say thank you for coming out tonight. Considering that there's snow on the ground, I expected the turnout to be a little suspect, but everybody remember that snow, nothing to be feared when there's snow, right? You just need salt for everybody. So as always, I'd like to thank a couple of different groups. Obviously, NumFocus for sponsoring the meetup itself, TD Ameritrade for sponsoring the location and the venue, and also Midas at the University of Michigan for sponsoring the food that you're enjoying right now. Always the important points, emergency exits for those of you who are new and maybe have come here before. There's an emergency exit right out here, an emergency exit right to the right of the doors that you came in through. As always, we're soliciting speakers. If you've got important or interesting talks to give, please reach out to us. We are planning in April to do another lightning talk, so look out for that. I know somebody, Remy, reached out to me today about giving a talk in the future. Also provide feedback. If there's things that we can improve on as a group, as a community, let us know. And you can always find everything that you're looking for on our GitHub page. All of the slides are posted there, all of the events, whatnot, so check it out. And regarding the talk itself today, unless your question is quick, please hold it until the end. And remember that you're in a borrowed space, so please clean up after yourselves, any of your garbage. And if you see some hanging around, help out one of your peers. I'd like to always read the PyData Code of Conduct. So PyData is dedicated to providing a harassment-free meeting experience for everyone, regardless of gender, sexual orientation, gender identity and expression, disability, physical appearance, body size, race, or religion. We do not tolerate harassment of meeting participants in any form. All communication should be appropriate for a professional audience, including people of many different backgrounds. Sexual language and imagery is not appropriate for any of our meetup events. Be kind to others, do not insult or put down other attendees, behave professionally. Remember that harassment and sexist, racist, or exclusionary jokes are not appropriate for PyData. Attendees violating these rules may be asked to leave the meetup at the sole discretion of the meetup organizers. But thank you for helping make this a welcoming, friendly event for everybody. And of course, a quick icebreaker. Maybe before I speak about this icebreaker, I should also say that a PSA for about Python around April 2020, Python 2.7, end of life. So remember that. So if there's any time, now is the time to upgrade and go towards Python 3. And related to that, for our icebreaker, choose somebody either to your left or to your right and tell them if you're using Python 3 or Python 2.
Oh, confession time.
Go ahead, real quick. Introduce yourself.
Python 3 for embedded system.
Okay, we're back. Thank you. We are back. So hopefully, if you can minimally take anything away from today, it is that you've met somebody that has similar interests. And that you might have to do some convincing, perhaps. I don't know. I'd like to also highlight a this month in data science. There's this funny, or interesting, I should say, article that came out, which is called the 11K hand data set. So you can use this data set maybe for biometrics or for, I don't know, gender identity, race identity, as you move towards a more using, your body to identify who you are. So this was, I thought it was an interesting data set that was made available. And then there was somebody reached out to me from Michigan State University, a student, Bhattacharya here. I think I missed them. But he's an assistant professor at MSU, and he's looking for postdocs. So he's a researcher at in the computational toxicology department. So again, this will be posted, or you can reach out and apply. So he's looking for a postdoc. And of course, next month in January, we have Scott Sievert from the University of Wisconsin coming to give a talk, and that is on Tuesday, January 9th. The same place. The title of the talk is Next, Machine Learning, Crowdsourcing, and Cartoons. And so with that, I'd like to introduce our speaker for today. So we have Drew Fustin from Chicago. Drew has a PhD in physics from the University of Chicago, and he previously worked at GrubHub as well as SpotHero, and now he is a consultant and contractor for a company called Automaton Data, and he's for hire as well. So with that, let's introduce Drew. Thank you.
And slipped on the microphone.
I will now. Thanks for reminding me. Let me do this guy here. Sorry. Boom. The cartoons talk sounds a lot more interesting to me. So mine's not going to be as well. I don't know what that one's going to be about, but it sounds fun. I'm going to be talking about time series, and specifically time series experiments. And what I mean by that is the same sort of idea that you would have if you did like an A/B test or something, where you take a control population, you take a variant population, you change something between them. Can you determine like what the effect size on the population that change had? Well, how do you do that in the case where you're in, like, say, time series land, right? The reason I wanted to do this is because I wanted to learn it myself. So at SpotHero, we had like a radio campaign, right? And so you have a radio campaign. It's either on or it's off. It's not like I can just like send it out to like this part of the population and not to that part of the population and then compare how it's different. It's either all on or all off. One way people get around that, sometimes they find like semi-identical markets, and they'll maybe use those as your control and test populations. But you can do this other ways as well. And it's not entirely tricky or anything. There's nothing super interesting about it necessarily, but just something I wanted to learn. So I'm going to talk through, there's just tons of slides, but I tend to just go through them fast. And I also like to kind of give talks where it's like pretty, I don't want to say basic, but like really builds from the entire ground up. So I'm hopeful that even if you're like a super expert in like time series stuff, I know there's lots of, sort of financial people that this is like their job. So if that's boring to you, I'm sorry. But so I'm going to talk about like typical experimentation in data science, what time series experiments are. I'm going to create some data that we can play with. Talk about ARIMA algebra and forecasting with the stats models package, which is typically in Python an easy way to do ARIMA forecasting, and then actually modeling like interruptions with PyMC3, which is an MCMC library that does simulations. So about me, that's me and my wife and kids. They're from my wife's from the Toledo area, so we have family Christmas this weekend. So came into town, dropped them off, and then came up here. So as Sean said, I was at the University of Chicago. I did a PhD in physics looking for dark matter. So I had to be like a miner and go down into like an active nickel mine with a bunch of Canadian miners, which is really neat because that's where our experiment had to be. It was like a mile underground. So that was neat. I most recently have been at SpotHero, which is, if you're familiar with GrubHub, it's just like GrubHub but for parking. It's basically the same company, so it was really fun to go from one to the other because I got all my ideas at GrubHub and then I went and tried to build them at SpotHero. So I left there about a little over a month ago now, and I'm doing like contracting consulting in the Chicago area. As for you, if I say something like hypothesis testing and A/B testing, does that typically sort of ring a bell? And everybody's like, yeah, that's cool, I understand. Same deal, like time series forecasting, something called an ARIMA model. No? Okay, cool. That's good. If I were to talk about like probability distributions, if I were to say like a Poisson distribution, something like that's cool. Anybody happen to know off the top of their head if something is Poisson distributed in, say, time, what is the distribution of the time between events?
Is it 0?
No, what's that? Exponential is correct, yes. So that's something we'll use. And then if I said Markov chain Monte Carlo, anybody? Okay. I just kind of wanted to get some nods or head shakes. Okay, so typical experimentation. You have A and B. You have a control group, which is going to get your normal website. You have your variant population. They're going to change the bar from red to green, and we want to see if that actually changes something like conversion rate, let's say. So conversion rate was 23%. Normally, they give them a green bar, and for some reason, people click on that green bar more. And then you want to kind of measure the difference between the 23 and the 37. And so usually you run these things concurrently so that meaning at the same time, so that you can keep all of the unnecessary variation controlled. So in Python, it's pretty easy. You have a beta distribution when we're talking about conversion rate, a beta distribution where you can draw from a measured number of successes, which would be something like conversions, a measured number of failures, which would be like the total number of visits minus the conversions, right? And in population B, the same deal. So you have like, do I have it written here? Oh, no, I don't. I'll show you in a second. And then what you can do is you can just draw from those two populations a group of, let's say, 10,000 samples, just measure the difference between those two, and then look at what the distribution of that difference is. And so an example would be if in population A, I had 100 observations and 20 successes, that would be a conversion rate of like 20%. In population B, I got 50 observations, 15 successes, which would be a conversion rate of 30%. Like, is that enough to actually tell the difference between these two populations? Well, you can actually just like sample from this, compare those two populations against each other to actually determine what the effect size is. And turns out that to 95% confidence, it's between -4% and +25% is the effect rate, right? So to 95% confidence, I cannot say with this many observations that it for sure caused a lift, but that's why you then would get up to like 60 or 70 or 80 observations, right? The more you get, the tighter this little green bar becomes, and then you can actually tell the difference, right? And so that is entirely done with just that code there, which is pretty straightforward. Just a couple lines of code, not too bad. So some experimentation is easy, right? I don't have the slightest idea why somebody hotkeyed the shift key for A/B testing, but there you go. Some experimentation is hard, and I love this GIF. An example being what we're going to talk about now, which is like, here's a time series forecast, right? And let's suppose at this sort of gray bar here that we introduce some sort of change in the population. Like maybe we launched like an ad campaign or something, right? And so the blue here is the observed, the green is the forecast, and you can see that as you get farther into the future, like this is the future here, and you're forecasting this, that your error bars of what you actually think the forecast is going to get wider and wider and wider, right? So it becomes more and more difficult to actually tell if this effect that's happening is actually from what I introduced, or if it's just from normal variation in the data, because normal variation is pretty wide, right? That's what these error bars say. That's normal variation. Yeah, you have a question?
Yeah, given the periodicity that you see in this, can you control for stationarity or anything like that?
Yeah, sure. And I mean, presumably this forecast here, I mean, actually no, because this is from a blog post by a guy named Tom Hogsberger, he's awesome. He definitely did, like, this is based on, like, just using pandas, because he's one of the contributors to pandas, using pandas and as well as stats models to do time series forecasting. And he definitely was doing all those, stationarity tests and everything else. So, So in a world like this, it becomes kind of hard to do A/B testing, right? And so you might think, nah, I'm not gonna do that. So what you actually do is maybe you have, like, here's your baseline. This is your normal population. You introduce some sort of change, and it actually changes whatever the event rate is. And that actually looks decently measurable. I could probably do something about that, So, maybe this isn't so bad. You simply just apply a variation in time, measure before versus after, and we can actually tell what's going on. So maybe we're a little bit relieved right now. I would say more common would be something like this. Ignore the red line for a minute. Like, there's no way there's like a change in that time series, right? Like there's like 15 observations here. And now they're going to say, oh, yeah. We introduced some legislation, and doesn't say on here, but let's just say, we see like a 10% drop in whatever this is. Like, no way. So you could say, simply, apply a variation in a moment of time and just like measure, So, yeah, that's how something like that would be. So let's give this a try. We're going to make some data that we can run through some sort of model. Okay, so I'm going to think about transactions. And so transactions are maybe even something like bus arrivals. The classic example of bus arrivals, buses are Poisson distributed in time, which means, hypothetically at least, that if a bus is supposed to arrive every 5 minutes, that's your sort of expectation value is 5 minutes. A Poisson also has the added characteristic that the variance in that population is also 5 minutes. That kind of defines the Poisson. So we're going to start with a homogeneous Poisson point process. Point process meaning these are points distributed randomly in time, like bus arrivals. Poisson means it follows some sort of distribution that looks like this. Lambda is my mean and my variance. T is the amount of time, the expectation value of the number of events I should expect to see, and an amount of time t is just equal to lambda times t, right? And the probability that n of t is exactly equal to lowercase n, just any number, is this, and that's the Poisson distribution right here. That's the PDF of that. Homogeneous just means that lambda is a constant, right? It's just the same all the time. And as we got with our quiz earlier, the differences between events in time are exponentially distributed with a factor of 1 over lambda. I'm going to use that fact here to actually create a homogeneous Poisson point process. This is all commentary here. This is literally like 2-3 lines of code, right? And all you do is you randomly sample some exponentials from an exponential distribution with some sort of rate, and you just cumulatively sum them. And so I have one that's maybe at like 2 minutes, and then another one that's like 4 minutes later, and so that would be like 2 minutes, and then 6 minutes would be the second event, and so on and so forth, right? And that is a homogeneous Poisson point process. But events aren't really constant in time, and so can we actually vary that lambda? That's what's called a non-homogeneous Poisson point process, which is where lambda is allowed to vary with time. So that might seem decently straightforward, but it's not exactly the easiest thing to like simulate in the real world, except for with complete laziness, which is you just make a homogeneous point process with some sort of lambda. Let's call it lambda h, which is the highest lambda that I actually want in my non-homogeneous Poisson point process, right? So it's the highest instantaneous rate that I want in the whole population. And then I'm going to attach a random number between 0 and 1 to every single point in the homogeneous Poisson point process, and I'll show you what that means in a second here. And I'm going to define some sort of rate function, r, such that that's between 0 and 1, so it's kind of a probability, such that r of some t is equal to 1 when, for any t for which this lambda is the maximum lambda, and it's 0 when it's 0, right? So, and then discard any points in the homogeneous Poisson point process for which this constant is actually greater than that R value. So, in picture form, here is some data. This is a homogeneous Poisson point process, maybe I think 500 points or 1,000 points or something like that. There's a whole bunch at 0 and a whole bunch at 1. So if I were to smush these all down, you could imagine that I would make like a histogram, and that histogram's heights would be Poisson distributed. So it would look something like that, I guess, if it were a histogram, although that's a line chart. I then have this sort of rate function here, which says basically at time t minutes, my rate's actually kind of small, whereas actually at time t20, the rate's a lot higher, right? So maybe this is overnight. This is like peak rush hour or something like that, right? So you just literally define a curve that looks like this, right? So it might just be a sign where it's like overnight it's low, during the day it's high, the night it's low, day it's high, and it just goes like that forever, right? And you just throw out all of those points above there, so all those red points, and now you have a process that looks like this. This is a non-homogeneous Poisson point process. So you can see that it's, sort of a low rate, and then it kind of gets higher as it goes out here. But the points there are homogeneous or Poisson distributed, and instantaneously they have a certain lambda, right? So building this, also not hard. I just build my homogeneous Poisson point process, assign some random numbers, and then apply some sort of thinning function like that red curve there, and then just throw out everything that's less than that, right? So, cool, here's my thinning function, let's say. This is overnight, this is during the day, overnight, during the day, and this is maybe the weekday. This is like weekends, right? Same deal, same deal, same deal, same deal. This kind of looks like what transactions would look like, let's say at SpotHero or something like that. And overall, there's maybe some sort of trend to it, right? SpotHero is doing better. We're getting more customers. It's growing in time, right? So this is what a non-homogeneous Poisson point process would look like, which really, really, really does look like the transaction data at SpotHero. So yay, and that's right, kitties. That data is going up and down. So let's talk about ARIMA algebra. ARIMA algebra is basically is what you would often use to do forecasting. It means autoregressive, AR, integrated, I, moving average, MA, and it looks like this. And my whole life, I've looked at this and thought, that's too complicated. I don't understand what's going on there. I'm just going to literally throw it at stats models and let it do its thing, right? Turns out I couldn't actually do that for this because I actually wanted to add some variation to this model, and so I actually had to learn what the heck was going on. So this is me at the beginning of this exercise, just the existential dread of, I don't understand what that is at all. But turns out it's actually decently straightforward. An ARIMA model is defined by three numbers, P, D, and Q. These are like the order of the autoregressive, integrated, and moving average parts, right? And we can simplify this down to, there's just this mathematical operator in their autoregressive world, which I'm going to call phi sub p. And it acts on b. B is like a lag operator. Basically, b times x of t would give me x of t minus 1. It just steps the time series back 1, okay? So that's the autoregressive part. This is the integrated part. This nabla here is just defined as 1 minus b to the d. We'll see that in a second. And then that's all equal to the moving average part, which is this little guy here. And then that's times the error in the observations at any sort of time. So you look at autoregressive. 5p is just defined as this. It's just 1 minus phi 1 times the backtick operator minus phi 2 times the backtick operator squared minus blah, 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 all the way up to p, right? So often if you have an AR1 model, it would just be this part right here. It's just 1 minus phi 1b, right? That's not so hard. 1 minus phi 1b, if it's AR1, let's ignore those two. It's just 1 minus phi 1b times x of t equals epsilon t, right? So that would be x of t minus phi 1, x of t minus 1 equals epsilon t, which is literally just an equation that you can solve. Not so hard. Integrated looks like this: 1 minus b to the dth power. You just take d consecutive lags. Yeah, and moving average looks like this. It looks exactly like the autoregressive one, except for just with a different thing, lambda instead, and it hits on the epsilon instead of the time. So you can actually generalize this to a seasonal by adding 3 more components, which look the exact same. It's just they're with capitals, and there's this little s here. And all that s does is it's just apply that to that b. It's literally b to the s power, right? And so a seasonal autoregressive, this phi p is again just like, well, that's an operator, but the phi 1 would be just like a constant that I'm going to solve for. And remember that, well, actually, let's use this one because the pink showed up a little bit better. So the theta q is 1 minus theta 1 bs, so b to the s power, and then the second term would be b 2s, right? And then all the way out to b ps, right? So if this was like a fourth order seasonal, that would mean that your first term is theta 1 b to the fourth, so I want 4 lags back. Your second term would be b to the 2s, which would be 8 lags back, right? So this allows these lags to be non-consecutive in time, right? So that's what the seasonal does for me, right? And so here's your model. That is a seasonal ARIMA. At least color-coded, it maybe doesn't look so bad. But at the end of the day, all you're doing is whatever the model is, you could literally just plug in what these mean here, and all you are left with is just an equation, and you can kind of solve equations. And then once you have an equation, what you're trying to do is you're trying to fit for what are these values here, right? And that's it. So it's literally just kind of a least squares fitting problem, right? Which isn't so bad. So an example being an ARIMA 110, you have phi 1b, nabla 1b, xt, theta 0b. Theta 0 is just 1, right? Because it's 110. That's what theta or phi 1 means. That's what nabla 1 means. You just carry these things through. B times b is actually equal to b squared, right? Because I backtick once and then I backtick again. So it works out to just be this equation, right? So if I come in and I have knowledge of what yesterday or 2 days ago value was and yesterday's value was, and maybe I observe what today's value is, I can actually measure what epsilon is, and then I can do that again for tomorrow and do that again for tomorrow, and you could just keep stepping forward in time, right? So that's what this is. So that's not so bad. This is us now. So forecasting with ARIMA. I took an aside and added some notes. I gave this talk actually on Monday, but I wanted to kind of talk a little bit. That ARIMAs actually want your time series, the errors in your time series, to be normally distributed, which often aren't. Like in our case, they're not because they're Poisson distributed, right? So you can do what's called a Box-Cox transformation, which is literally just this formula here. I only say this because you'll have to do this when you're doing forecasting oftentimes, and that's really easy because you just import it from SciPy, and Box-Cox on your time series literally gives you the transformed time series and then some sort of exponential.
Is it automatically find you the value of the Box-Cox?
Yeah, it finds you like this minimum value, right? And the way you actually find this minimum value, if you want to do it by yourself, is you would just pick a bunch of exponents, and you would figure out what the transformation is for each one of the exponents, and you just pick the one that has the minimum variance. That's minimum variance from normal, or whatever it is. All you're doing is just minimizing that. And yes, this does that automatically. Other thing you need to know with forecasting is these autocorrelation functions, which these are the tea leaves that you read when you're doing time series forecasting. So I borrowed this from from Tom Augsburger, who I mentioned earlier, which is just using the stats models, plot ACF and plot PACF, but it's this little thing that spits out everything all together. And so here is, for instance, a simulated data set, and this is what the autocorrelation and partial autocorrelation plots look like, right? And the name of the game in forecasting is we want to get rid of this little gray bar here is basically noise. This is like I can't tell the difference between this and 0, and I want this to be 0. What I mean by that is I want this to be white noise. I want it to just vary around 0 and have no characteristic to it whatsoever. Any one of these dots that's outside of this bar basically means there's some component to it that's not quite white noise, right? And so what I want to do is I want to get rid of that, okay? And so that's what the tea leaves are. So ACF being so high for so long, you just kind of learn these things as you go, I guess. But it suggests that an integrated model is needed for this particular thing. The other thing that would tell me there's multiple things. One, there's definitely a trend to this. That's usually what you kind of do differencing is to get rid of that trend. And so that would suggest I probably want an integrated term. So with this autocorrelation here, also you can measure stationarity, as you mentioned before. There's something called an adjusted Dickey-Fuller test, which will tell you basically if there's a unit root, which has something to do with stationarity. If there is no unit root, then it's stationary, otherwise it's not. This value here is a p-value, sorry. It's a p-value, and so if that number were less than 0.05, I guess, then I would be able to say, yeah, this is stationary. The fact that that number is not less than 0.05 means it isn't stationary, which means I need to get rid of that, which is what I would use like an I term for an inter-ARIMA model. So going back to our partial autocorrelation here, we have these spikes that happen at 7 and again at 14, and you can also see them over here in the autocorrelation. It's just higher at 7 and 14. Seems to suggest there's some sort of seasonal trend with like a 7-day component to it, right? Every 7 days, the trend repeats, right? So if you remember from our little rate like thinning function that we defined earlier, that it was like Monday, Tuesday, Wednesday, Thursday, Friday, were like this, and then it went down for Saturday, Sunday, right? So that's what this is picking up. Okay, so that's going to suggest that I want some sort of seasonal term with like s equals 7 here. So let's just try a seasonal ARIMA with like 0, 1, 0. 1 meaning I need D to be greater than 0, so why not 1? S is equal to 7, I know. And I don't know, I just picked 1, 0, 1 here because sometimes if you pick other ones, it just doesn't actually convert and it doesn't give you any model whatsoever. So to do this, real easy with stats models, something called Saramax, which sounds like a villain from Lord of the Rings. But you just pass it a time series, give it your order and your seasonal order, so 0, 1, 0, 1, 0, 1, 7, and that's it. And then you fit the model, and then it will spit out some sort of, the residual will spit out some sort of, actually I think that's the result, spit out some sort of summary, and it will have all sorts of things to it. This right here is called AIC, which is an archaic information criteria, which basically says, is this a good fit or not? But you're punished for overfitting. So the more terms I add to it, the worse that number will get. If, of course, the log likelihood of that fit doesn't overcompensate for adding those terms. So two models that behave the exact same and predict the same, one having 2 and one having 3 terms to it, the 2 will have a better AIC. Better meaning lower. So in this case, 1395. If I were to compare this to another model and it had like a 1200, I would say that model's better. Right? So also spit out here is my capital Phi 1 and my capital theta 1 here. And so here's their best guess on that is basically 1 with no standard error, and -1 with no standard error, basically. So that's cool. It at least converged on a really very specific answer. And if I were to look at what our time series looks like now, with this applied to it, that looks pretty white noisy, right? It's not so bad. It's not white noise, though, because you can see that I still have a couple dots that are outside of my blue, and I really have one dot here that's outside of the blue here. And so that suggests to me that there's something more going on. right? So I actually want to add more terms than just this to get rid of everything, right? So this being way far down, but all the rest of them being pretty much nothing, suggests probably a moving average, because it turns out that like a moving average 1 is memoryless, which means that it remembers like the error on its last step, but forgets about it 2 steps beyond. And that's not true of a autoregressive. Like it keeps its memory along and it kind of just decays the farther out we get. So that would suggest I at least want to add a 1 there. This also sort of suggests that maybe I want an autoregressive term here, because the second term, just believe me, you can try things if you want. Let's try, in fact, a 2-1-1, because it turns out that one worked really, really well. Much better AIC. Here's my values that I would get here. That's okay. It looks real good. All of these things are within the blue. I think that's a real good model, right?
Are you still getting autoregressive and other coefficients close to 1?
Oh, yeah. No, so these were the 2 that I had before. Yeah, actually they are. They're the same.
Warning sign.
That they're the same as...
No, that they're close to 1.
Oh, that they're close to 1? Yeah, right?
Yeah.
Yeah, you're right. And I hadn't even thought about that. So that's true. That's weird, though. Well, that probably would suggest to me that I want one of those, but not the other, probably. Because I definitely want a seasonal term. I know that. But so probably overcompensating having both of them.
This is the residuals?
Is what the residuals?
No, the plot and the...
Oh, yes. Yeah. So, yeah. And so that's the white noise that we want, right? That's a pretty good model. So forecasting with ARIMA. I don't know what GoBear is, but I love it now. The whole of forecasting with ARIMA, and I don't like the outcome of what's about to happen, but this is what you would do. You would maybe box-cox transform some things. You would get some predictions out of our forecast that we saw a couple slides earlier, turn those predictions into the proper original sort of scale that I had, and just plot that. And so here's your forecast versus your your observe versus your forecast. You can see that it's not terrible in that it kind of trends the right way, and the gray bar is getting wider as I go out farther in time. This is like where I'm forecasting from right here. Really don't like that. I'm pretty much missing the weekdays all the time. Like, I'm definitely underestimating the weekdays, so I would want to explore this more, but that's kind of the output of what a forecast model would look like, right? Cool? So that's forecasting in ARIMA. Interrupted time series, so now this is what we're actually trying to talk about here, is I want to introduce at some time t some variation, right? And that variation maybe has an effect size beta, meaning if my time series, like if I was getting like 100 transactions normally, like on a Monday, let's say, and let's say beta was like of size 20%, I might expect that I'd get 120 next Monday or something like that, right? And that would be because I got a lot more users because of a radio ad or something like that, right? And so that's what I'm wanting to measure, is I want to figure out how strong is beta, right? I called it beta throughout. I was using this textbook. In fact, he has this, and I know you can't really read this, but an omega 0 is what he has it called here. So he basically has a model here. This is, by the looks of it, a MA1 model, right? Because he has... no, it's not. It's an... I don't know what it is. I have to look. Oh, no, it's not anything. It's a random walk model is actually what it is. But what he does with it is he measures what would omega 0 be to actually match this time series here versus here, right? And with 2 different kinds of models, and he gets like minus 1.5% basically in both of them. So hooray, like that's 1.5% lower than that. Like, and yeah, like with like pretty good, t values and all that jazz. So I don't know. I'm skeptical, but yes. So that's what that is, and all of this is literally, as we said earlier, just doing our normal like least squares sort of regression, and this is my equation for the model here, right? So in our world, we're going to start with a simple time series because I don't want to do something super complicated. So I'm just going to have my non-homogeneous Poisson point process just being a thing that increases with time. After 365 days, like my transactions double or something like that, right? So it's just going to look like a growing trend, and that's all. I'm going to add like a small effect size at some start time, which I call treatment start, and I'm going to say, so the time series starts on March 1st. The treatment starts on May 1st. So on May 1st, we launch a radio ad, right? And I'm going to posit at the moment, for illustration purposes, the effect size of this radio ad is exactly 10%, right? So if I had expected 100 before, I'd get 110 now or something like that. And this is just messy pandas just to make a time series that is what it was before, and then I just add some beta to it. And then I'm going to throw that at my ARIMA model just to see how it works. Turns out a 0-1-1 model works really well for this guy. And get my predictions and just plot them. So this would be our data set we're going to work with. So here's your data. Here's what the forecast is of that. These are the error bars of the forecast. There's 95% confidence bands. 1, 2 are outside of my confidence bands. There's probably about 100 terms there. That looks, 5%, that's all right. Red is with my effect in it, right? So the idea is, if this time series were to just keep going on in time, I should probably be able to measure this much of an effect here, right? And so I'm going to make one observation and say, wow, that number's kind of big. And then second observation, that number's really big. And then what is the best fit value for this beta that would give me these values here, okay? So that's what I'm going to do here. This is with PyMC3. So this is probably small for at least you in the back. Does this just look horrible? Yeah, well, you can find the slides later. So with PyMC3, what you do is you define a model, and you define some variables in that model that you seed with some distribution to them. And then what it's going to do is it's going to pass through thousands, let's say, of passes through here, and it's going to sample from those distributions and eventually find out, actually, this is where that distribution should be. I started at 0 with a standard deviation of 2, but it turns out that, when all's said and done, theta kind of shifts over here and settles onto some good value. But it gives you, the error bars around that. So not only am I going to get, theta, but I'm going to get, my confidence band around theta once I fit my model. So this is my ARIMA theta here, right? This is a 0-1-1 model. That's my theta from the final one there, right? And then I have this beta term here. So the beta term, okay, so first of all, PyMC3 is built on top of Theano, rest in peace. Theano is just a way of doing tensors and stuff, and they use it for deep learning, but I'm just using it for tensors. Tensor is just a fancy way of saying a vector, but in more space than that. But in this case, they're literally all just vectors, so it's unfortunate that I couldn't just use vectors. This switch value here is just a case statement. It says, if this thing is true, use that first one. If it's not true, use the second one, right? And so I'm going to create a time series, and that time series is just y. It's my normal time series, unless, of course, y switch is false, in which case it's going to be y minus y times beta, right? Where beta is a number sampled from this distribution, okay? So, and that switch is just the cutoff point of when the experiment starts, right? So everything to the left of when the experiment starts is y. Everything after the experiment starts is going to have this y minus beta here, right? So if I only threw data at this before the experiment, I actually would never be sampling on beta, never be figuring out anything better about beta. And what I would get out the other end of this would be that my best guess for beta is a normal distribution centered at 0 with standard deviation 2, because I haven't given it any observations to update that understanding, right? So this here is my ARIMA model. So this is why I had to learn how to do ARIMA algebra, because what you are going to do in this model here is you're literally going to, I'll just skip ahead here. Looping in Theano also is weird, but it's basically, it's this. It says, I'm going to give it a function called calculate next, and that's going to output some epsilon value, and I'm going to be going through and calculating my epsilon. I'm going to calculate my error terms as I go. I'm going to seed it with some initial number, which I'm going to say is 0, and then I'm going to pass it through this function, and every time I go into this function, I'm going to say that the error is equal to the current value of y minus yesterday's value of y minus theta times epsilon, which is actually yesterday's value of epsilon, right? And how I derived this equation is from my ARIMA algebra. 1 minus b times y of t, 1 minus theta b times epsilon t. You work all that out, and epsilon t is equal to this function here, which is that function there, right? If this were a different model, like a 1-1-1 model, it would have different terms here, and this would look different. Right? So this is very specific for a 1-1-1 model, or a 0-1-1 model, and I used that particular model just because I passed it through stats models, and it said, this is a good model. And so I was like, okay,
it's also an exponentially weighted moving average.
Also, it's an exponentially weighted moving average. That is
very helpful for intuition.
Yes. I mean, that is literally what it is. It's growing exponentially with time, and otherwise it's just like a...
The weights are
Yep.
exponential.
Yep. Yeah, so basically then you pass this model here. You say with build model equals my time series when the time series starts, and I'm going to give it like a number of treatment observations. So I'm going to say like I'm 2 days into my treatment. I'm 2 days like past like I'm on May 3rd now. I've observed May 1st and I've observed May 2nd. Okay, and so I have those two observations. Let's go back here. One more. I have these two observations here, boom and boom, right? And I'm going to say, hey, what do I think beta is now, right? Before I had those, I think beta is 0 with some sort of unknown confidence. Now I think beta is 0.2. This is a bug. I wasn't able to figure this out. This should be 0.1, and I swear to you, on the whole drive over here, it was 0.1. And then I was like trying to update the slides like just now, and it kept being 0.2. I don't know why. So I'm going to try to fix that. But it was really great, and it was like zeroing right around this. And I mean, like, that's crazy zeroing, and I don't trust how, like, after 2 observations, it's between 18 and 22. You know, like, come on. But theta is really good. It's actually pretty well the exact same theta value that I got from my stats model before, right? So, except for now I actually have a spread to it. Like, it's not just like, oh, theta is equal to minus 0.8. It's somewhere between minus 0.83 and minus 0.81, you know, to 95% confidence, which is really cool. This noise here is exactly what you want to see. That means that that's the tingling that means it's working, right? So that's the PyMC3 is doing its job. So I've now made, with this model here, an effect size observation, right? So how good is my radio ad? It's that good with this confidence, right? So that's actually really cool, because that's exactly what you would do with an A/B test where you're trying to measure beta. Why did I use beta? Because beta is the distribution. Anyhow, you're trying to measure like what the effect size is between the control and the variant, right? And that's exactly what we did here, except for it's in time series land, which is cool. So, hooray, celebration. That works pretty well. And that is all of my notes. It was like 79 slides, too, which is amazing. So there. This is all my stuff again. This right now is here, but you said you're going to host things as well, so you can probably just clone or fork this eventually. But I'm going to try to figure out that bug. Otherwise, it looks pretty good. So cool. Thanks, everybody.
We have some time for some questions, if anybody... Yep.
At the beginning of the talk, you talked about how you had put off learning Amira algebra, what was kind of your criteria or justification for using it instead of just downsampling and taking an aggregate function?
Downsampling and taking an aggregate function.
Like, what made you need the granularity for the interrupted time series?
I wanted to have something that was general enough that it could actually, like, I could throw it at any sort of time series and actually get like a good estimate of what that beta is. Because usually the time series looks like kind of what I had before, which would be like a seasonal 7-term, whatever. In which case that function in the PyMC3 would be really ugly and complicated, which is why I simplified it. But I'm not sure. I mean, there are a lot of other forecasting methods, and I recognize that I have a little bit of a Frankenstein's monster here of using like ARIMA, which to some extent is a pretty what's the word? Frequentist statistic sort of way of doing things, and then I like throw like Bayesian ways of doing things, and that's just because I wanted to use PyMC3 ultimately at the end. There's lots of forecasting models that do, forecasting using more Bayesian techniques as well. I just started doing this with ARIMA and had a book that was doing it in ARIMA, and then I was like, well, I actually want to get a little bit better of an estimation than that, so that's why I use PyMC3. So it's a little bit all over the place.
You use more of the data when you instead of downsampling. What are you saying? So you can use all of that instead of sampling.
Yeah, I'm not entirely clear on what like the downsampling. I know what downsampling means. I just don't know what it would mean necessarily in this context and how one would.
Like taking an average is really common for a longer period of time.
Yeah.
So you don't get the same granularity of detail as what you get there.
Right. Right. I mean, I definitely assume that like after, and I don't trust this right now as it is. I think there's a bug in there, but like after 2 days to be able to say, yeah, that's good, and then like on the third day come back and get an updated observation. Like, I think if I were to just like draw like a line through it, sort of thing, that I wouldn't necessarily get that granularity. Although if you look at it, the forecast that comes out the other end with a 0-1-1 model is just a line. But yeah, so yeah.
Did you have a question, Olga?
Yeah.
Yeah.
So have you heard about synthetic controls? Can you comment on the difference between systematic?
No, I have not. Have you?
Yeah. So
Can you?
the idea is like you say. So suppose we have this ad, and we are searching for another state or a city that looks pretty similar. Mm-hmm. But the idea is well, it's really hard to find one city or one state, so we just combine a lot of states, mm-hmm. the trends in the states, and we match exactly the trend in our state, for example, mm-hmm. and then we see after this ad started, if it's synthetic state, how it's going to behave compared to the real one.
Right.
So it looks kind of the same idea. So we just want to find the beta effect.
Yep. My initial thought on that was oh, well, this would be cheaper though. But in this case, no, the variant is still the one city, and the rest of the population is the control.
I believe it just works better if there is something else going on that affects all of.
Oh yeah. Yeah, and that's why this seems scary to me in general. There's a holiday, and I didn't actually take it into account and forecast it correctly, and I was just measuring the holiday, not the radio ad. Yeah, that as well. So,
any other questions?
Quick question. Have you thought about using a Remax model and flag the days that there were ads as 1 and the rest as 0 and see the effect?
Flag the days that are what as 1?
That you had the campaign and the rest of the day that you didn't launch the campaign as 0 and then see if the coefficients are significant or not.
Yeah. So that's another. So I think what you mean is actually vary it each day and turn it on, turn it off, turn it on, turn it off, and be able to really get some.
So
that's not what you mean? Okay.
You launch. You know that you launched the campaign from a certain day until and then you just flag those days as 1 and you regress it with the ARIMA. So using a Remax model.
Mm-hmm. ARIMA X is what he's saying.
Yeah.
That's where you add a covariant to it.
Oh yeah, actually, and that is what I was using, but I wasn't using the X at all. So I was using Saramax, but it wasn't with those exogenous updates to it at all. No, I could, yeah. Nothing more to add to that, but yeah. Yeah. Question? Yeah.
This is probably just purely academic, but how can you apply multiple seasonalities? Like you have weekdays, but then you also have like, say you're looking for parking spots in Ann Arbor. Certain times of the year you're going to find something, and certain you're not going to find any until it's landing.
Yeah. Well, because I've always been afraid of like all the algebra of this in the past, like what I would have done in that case would have been said, just take the Mondays and have a time series forecast for Mondays, and the seasonality there would be 365, let's say, or something like that. And then take the Tuesdays and have another one like that, and then again just combine all those together. And I've done that. I'm pretty sure you can add multiple seasonal terms here, because that pretty well, like, I mean, it just, it seems pretty commutative, where I could just keep adding other terms, switch them around however I want, and it would be fine. So, and you're nodding your head yes, so the answer to that is yes, you could totally do that. Now, with stats models, like, seasonal ARIMA wasn't even like available in like the master version of stats models until like the last year, which is crazy to me. It's always been available in R land, so you've got that going for you. But so if you're going to use one of the built-in packages, I don't think they sort of allow you to do multiple seasons, but that's why you learn how to actually do it from scratch.
Any other questions?
Yeah.
Maybe this was already sort of answered, but did you build a separate model like just for weekdays, and then build a separate one just for weekends?
Yeah.
Or somehow, I don't.
Yeah.
You can divide it other ways, but somehow, how would you piece those together?
I mean, I would literally piece them together by just piecing them together, and like eventually, like, oh, here's your Mondays, here's your Tuesdays, just like have those data frames of forecasts, and I would just literally append them and then sort it, and then be like, oh, look, there's. But yeah.
Would there be an advantage to that? I guess I'm thinking it might be easier to like.
Yeah, I mean.
Forecast if you have a.
Yeah, I mean, yes, but also remember like our like AIC, where we're like, hey, let's get the minimum number of terms that describes this time series. And if I were to say split it up into 7 independent time series, each of which is an ARIMA, let's say 111 or whatever, right? Which has two parameters to it. I now have like 14 parameters describing my whole like time series. Like 2 parameters for Mondays and 2 for, and that seems probably like overfitting to me. So I would want to probably figure out how to do like some sort of aggregated AIC or something like that to make sure that that actually is an okay model to do. But yeah, that feels just like a hierarchical model in that case, right? Which is basically to say you have an extra term which defines the hierarchy, which in this case would be, I have a model for Monday, and I have a model for Tuesday, and that's Monday and Tuesday are the hierarchy, right? So that's probably also where I'd go with that.
Last questions? So with that, I want to thank Drew, because now I have to improve my time series game, as well as my GIF and my meme game.
No, the GIFs, yeah. No, that's what I'm actually proud of.
And also, I want to point out real quick, this is sort of unrelated to this, but before we thank Drew, is AJ in the back had a request. You want to put up your hand, AJ? So if anybody has any expertise in using random forest, I think AJ could use an extra eyes on that. And somebody left their hat in the back. Thanks. Thank you. So with that, let's give Drew a round of applause and thank him again.